And so today I wanted to talk about.
Can you go to presentation mode? Perfect.
There we go. Okay.
All right, thanks.
Okay, so thank you, Michael, for the introduction. My name is Clark Newman. I'm with the Gateway Mission Design Team down here at Johnson's Space Center. However, what I'm talking about today has nothing to do with the NRHO. This is something that we're kind of doing on the side in the AI labs. And it's going to be using FreeFlyer. It is using FreeFlyer, and it is optimization and reentry predictions using FreeFlyer. And so this is kind of a precursor to the applying machine learning for atmospheric modeling. And oh geez, wrong button. All right, so to put some background to this problem, the satellites in low Earth orbit experience a minimal but non-zero drag. And so without maneuvering, low Earth orbit satellites will eventually re-enter the atmosphere and be destroyed. The atmosphere itself is very chaotic. So as a result, modeling the effects of drag on spacecraft in orbit is pretty imprecise. Usually spacecraft are usually modeled as with a quote unquote cannonball model that has a single incident area and single drag coefficient. And so as a result of the chaotic atmosphere and the simple modeling of spacecraft, we end up with large dispersions on re-entry estimates. And so what that really means is if you're tracking a mission that is in low Earth orbit, is expected to re-enter at some time in the future, we want to try to refine the estimate of when that is. And so there's a lot of orbit determination that can be involved, as well as propagation through numerical propagation through an atmosphere in these orbits, and then also modeling of the atmosphere itself. And so what I've got here on the right is a plot of the F10.7 centimeter radial flux from the sun. And these are in solar flux units, which is, I guess, specific to this application. So what we see here are, showing my cursor, the previous 5.5 solar cycles. And so this is pretty recent, coming up to 2022. And you can see that we are just beginning to increase the solar flux in the F10.7 regime. And our previous solar cycle, which started in about 2009, can be shown here. And you can see how it was much weaker than the previous 3 solar cycles, which was a bit of a surprise if you're working operations. And you'll also can faintly notice that each of these, even more pronounced in these later solar cycles, have a kind of double hump feature. And so there's definitely a highly chaotic, very noisy, but definitive signal in the solar flux that we want to try to characterize, capture numerically using smart tools. And so in comes FreeFlyer. And what we are starting with is a kind of standard approach. My controls are blocking my own view. Okay. So we have a kind of standard approach to how we can estimate a satellite or vehicle or any object's reentry epoch or date based on observations of how it has performed in the recent past, and then we can predict that into the future. And so the most simple, straightforward way to do this for any satellite for which you don't have explicit tracking data for would be to grab the 2-line elements that are published on it from a source like SpaceTrack or CelesteTrack, which have a enormous database of 2-line elements for every orbiting object in low Earth orbit that has a radar cross-section of 10 centimeters squared or above. So we have this enormous database of 2-line elements, which each 2-line element is a noisy observation of the spacecraft state. But for a lot of these objects, depending on its, I guess, visibility and depending on its proximity to other assets, they could be tracked pretty heavily and reported TLEs pretty regularly, or they may be tracked sparsely and only updated on the 2-line element database sparsely. And so looking at this chart here, I'm showing a kind of hypothetical reentry problem being solved, kind of in as you would see it being worked in the system or in FreeFlyer. And so what we're looking at here is the height of periapts over time. And on the left half, to the left of the dotted line, which would be, we could kind of denote as a hypothetical present time, we have all these noisy two-line element data, which give you a corresponding altitude of the low Earth orbit. And you can tell with those X's that they're slightly decreasing in altitude, but it's a pretty noisy data set. So we are using the FreeFlyer optimizer to regress, to do a regression fit of the ballistic coefficient on this initial state of these observed two-line elements, so that we can create a ballistic coefficient estimate onto the final two-line element state, and then propagated forward in time until reentry. And it could be propagated forward in time using different solar flux models, which will then create dispersions on your estimate or your reentry estimate. So you can kind of see in the bottom right here, we have what looks like a early, middle, and late estimate based on the drag coefficient or ballistic coefficient that we have estimated, push that forward in time until reentry. And then we have our kind of span of reentry epochs that we could expect based on the data we see. And so looking on the right half of this chart, or I'm sorry, of this slide, we'll see actual FreeFlyer code. And I've highlighted a few lines that show the actual optimizer, the actual interaction and execution of the optimizer. So you can see the whole thing is within a while loop. And let me pull out the cursor here. So the whole thing's nested in a while loop. While the optimizer has not converged, it will repeatedly loop through this definitive span of, it will loop through this definitive span for which we have observed TLEs, and take the difference, the squared difference of the altitude of the observed TLEs against a propagated spacecraft, with the drag coefficient being one of the state variables to be altered or to be controlled within the optimizer. And so in this line here, you can see that the state variable value being assigned to our definitive propagated spacecraft drag coefficient is coming right out of our optimizer. It's then propagated through the definitive time span. Its error squared is tabulated, summed up, and then averaged across the number of TLEs that we've observed. That gives us an average error squared. That is what we are trying to minimize in this definitive span. And once we achieve a kind of propagated state that kind of threads this needle and sends us from our first to our last state, or rather minimizes the errors across this whole span, we'll take that and then propagate it forward. That would be the second step. And so let's see here. So I want to show a video of the guy working. And so I recorded it in FreeFlyer and then sped it up 10x. And now let me actually start it over. And we can watch this guy, and I'll kind of speak to it as it's going. So now we're seeing it actually run the optimizer, and these green lines being cast out are propagated spacecraft that are being compared against the two-line element altitudes that are plotted with the white boxes. And so let me pause it right here. And so you can see in this console on the left, as it's refining its drag coefficient, it's reducing its roots on the RSS of the error in the optimizer until it kind of converges by virtue of not changing by 0.1% over multiple iterations. Once it's gotten to that point, it says I'm converged, gives you an estimated drag coefficient, and then applies that to the final state. You can see it coming right off of that final definitive state, and pausing it one more time. It runs all the way until reentry and gives you a reentry epoch of February 22, 2018, exact date, time if you care. So to add a little bit more context to this, the specific spacecraft that this is looking at is the Tiangong-1 Chinese space station, which did an uncontrolled reentry and actually re-entered in early April 2018. And so this just did a curve fit over a span of about 300 TLEs towards the end of its life. And so the next thing that this optimizer routine does is kind of shift that window forward by 100 TLEs. So now we're looking at TLEs 100 through 400 of the set. And now you can kind of see those being plotted here. And if I once again play, it's repeating that process, sliding that window forward in time, coming up with a new drag coefficient. You can see it running through its iterations and going down that gradient descent. Now it's now kind of converging, not changing. Now it has a new, let me pause it again. Oh, oops, I'm hitting the wrong pause button. How silly. Pause it again. And so you can see that our estimate has actually shifted forward in time as we input a new 100 new TLEs. And to be clear, we are kicking out the first 100 TLEs, adding 100 newer TLEs, and repeating the process. And so that's happening again. We shifted the window forward again. And this time you can see that the two-line elements, the altitudes as reported, observed by the two-line elements, start to kind of slip above where our previous propagations have estimated it to be. So this could mean a number of things. At this point, that space station was uncontrolled. Its attitude could have changed. Something in the atmosphere could have changed. But as a result, our third reentry estimate, which again, another, I guess, 200 through 500 TLEs, 200 through 500 of the 600 TLE set, shifts our estimate forward again. And this time it's actually really close to the actual reentry epoch of, I want to say April 18th or April 12th. So we're running it. It's going to run it again on the last 300 TLEs, and then a fifth time using the entire set. And so what this aims to demonstrate is the transient nature of training on, training any kind of system to estimate your drag coefficient on a variable atmosphere. There's a lot of temporal changes to consider. So we're now done here. So these 3 and 4 estimates, 3 and 4 were a lot more accurate. They moved it later in time. When you consider the entire set of 600 TLEs, it gives you a solution. It actually backs off a more accurate solution. And so what that shows is you kind of want to introduce the concept of memory to this, where you kind of ignore older TLEs as your conditions and situation have changed, and you want to more heavily weight data closer to the present. And so this was kind of a proof of concept to show how we can use TLEs to solve the reentry problem. And so the next steps, the forward work for this would be to actually introduce machine learning concepts where we have this wide database of, wide and deep in terms of across many missions and just objects, as well as across many altitude spans. So what I was just showing was very low in the atmosphere. I can go back real quick. And so you can see not long after our curve fit does this guy really fall out of the sky. So we're talking about just a few months of propagation. But we do run, in a previous job of mine, we would do reentry analysis on current missions that are still up at 700 kilometers altitude and such. And so being able to have training data that runs the gamut from 800 kilometers to 100, we want to be able to throw all of this noisy data as a training set into a machine learning concept. And so the two that we've kind of are circling around right now are physics influenced neural networks and long short-term memory algorithms. And this is where it's kind of reaching the edge of my expertise, where we can kind of use these concepts to create an atmosphere model that adds a kind of additional small force to the normal exponential decay atmosphere. So that when you propagate through this machine learning trained atmosphere, hopefully you will have some additional predictive accuracy value that can come from this atmospheric model, either for the reentry, for the actual reentry problem here, where we're trying to either verify that a satellite will be disposed in a timely manner, or just understand how a satellite is behaving if it's not cooperative. So there's many applications to the actual atmosphere model that can come out of this. So this forward work is just kind of putting that into a block diagram of how we would do the process of scraping our TLEs, turn them into inputs, train a model that interacts with FreeFlyer, where we're kind of going between our machine learning layer and the FreeFlyer layer to actually propagate through this machine learned atmospheric model layer. And so this is basically the concept of that we are starting to get busy on now. So that's kind of wraps up for me. I will now take questions.
Great, thanks, Clark. Machine learned atmospheric model layer. I'm looking forward to the acronym for that one. It sounds like a problem in need of an acronym.
Yeah, that's going to be actually our first order of business, is to spend most of time on that.
Excellent, excellent.
Yeah.
Questions that we have. First of all, the analysis that you showed in FreeFlyer, is that analysis running serially? Could you parallelize the problem?
Yes. Now I want to go back and show. Yeah, because we're doing the same process to I guess to each mission or object. This kind of process could be done on. And so if you have I guess what we're trying to figure out right now is our subset of mission satellites that we would kind of look at. And among those, you could parallelize this. And definitely one of the later goals, to create a kind of whole system that is continually trained would probably necessarily need to be parallelized if we are trying to scrape TLEs and process across hundreds of missions. I mean, that the parallelizing then becomes very important. We're doing the same thing across many missions. I don't see why it could be parallelized. I guess one thing that could kind of put a wrinkle in that is that the stochastic gradient descent, we'll be doing kind of mini batches of crunching a few at a time. So we'll have to kind of figure out, because this is all feeding into the same machine learning model, when do we update, how often do we update the model and then go back to our data, or how big are our mini batches for stochastic gradient descent?
Gotcha. A couple questions about this model. So let's stay on this slide. Question: does the error in the optimization objective have a physical interpretation or meaning? Yeah,
so we are looking at the altitude of the spacecraft at the epoch of the TLE, and when you string these along in time, they should, this TLEs are noisy, but if they were not, they would kind of give you a perfectly, not perfectly straight, but they would give you a contiguous state as the satellite decays. And so if you are above or below that, that would let you know that kind of tells you if you were modeling your atmosphere too dense or not dense enough at that altitude. So if you are essentially above where you thought you were supposed to be, then your atmospheric model is not incurring enough small force.
Gotcha. Another question about the setup here. You talked about the ballistic coefficient, and just thinking about the data that you get with the TLE, do you need to know, or would things be better if you knew the mass or the cross-sectional area for the spacecraft?
Oh, yeah, definitely. And I think one kind of thing that we are consciously, by we, I mean, this, I'm the only one kind of looking at this right now. We're actually getting more people onto it, but absolutely. The more information you have about the spacecraft parameters, then you can tease out um, effects from atmosphere interaction versus the spacecraft itself, or its own parameters. Um, at first, though, I wanted to try to make the system, and this will be at the expense of accuracy, possibly, is agnostic to all that, because we're going to be pulling from a huge database of many objects that are just could be kind of wildly different from each other or non-cooperative. We just don't know, either foreign assets or objects of highly variable shape. So that would be something to look into, and maybe if we can kind of also apply this, and this would be a fun project for someone, also apply this where we can augment the knowledge of the spacecraft we know from just TLEs to we know TLEs plus these few parameters, and that could easily get you, I guess, that could possibly get you more information out of the TLEs you have. And so yeah, but for the first pass, I'm kind of relying on the fact that there are millions of TLEs available, and that hopefully you can just turn the crank enough and all that stuff washes out. But we'll see.
Gotcha. Have you thought about using FreeFlyer's flat plate modeling capabilities at all for this analysis?
No. The short answer is no. We've not thought about using that. I think kind of similar to the answer of the previous one. My concern is, again, getting away from being agnostic to the inputs at the expense of improved accuracy, while we're at the same time making assumptions about the shape of a spacecraft or object could introduce biases and errors that you need to be careful about. So that may be kind of a bit of a hand wavy excuse for why we would not do such a thing, is to introduce plates that are not really there.
Gotcha.